Hey guys, welcome back. We continue with the book Python for Data Analysis, and in this video we are going to learn about NumPy. If you want to follow along, feel free to subscribe to the channel, and let's jump right in. Let's dive into the NumPy basics. We're going to cover arrays and vectorized computation. If you want to follow along, you can head over to wesmckinney.com/book. The link is also in the description down below. Now we are going to cover the basics of working with NumPy. In a later video, we're going to dive deeper into some advanced topics. We're going to start out by covering ndarray, which is a multidimensional array object that NumPy provides. Then we're going to dive into pseudorandom number generation, and we're going to learn about universal functions, which allows us to perform fast element-wise functions. After that, we're going to focus on array-oriented programming with arrays and learn about file input and output using arrays. We're also going to cover linear algebra briefly, and we're going to look at an example of a random walk. NumPy, which is short for numerical Python, is one of the most important libraries that Python provides for numerical computing. A lot of computational libraries that use scientific functionality use NumPy's array object, and it's considered one of the standard interfaces for data exchange. And a lot of what we learn about NumPy can be applied to pandas as well, so it's really important to understand NumPy. Now, one of the reasons why NumPy is so important and so popular for numerical computation is that it's really designed for efficiency on large arrays of data. So for instance, NumPy's library of algorithms is written internally in C and therefore can be executed faster than a solution written in Python. Additionally, NumPy performs complex computations without using Python for loops, which can be quite slow if you have a very large dataset. And therefore NumPy is faster than regular Python code because again we are using C-based algorithms rather than using regular interpreted Python code. Also, NumPy provides a well-documented C library, so it's quite easy to include code written in C, C++, or Fortran, for instance, to improve the performance. And to better understand the performance difference using NumPy versus regular Python, let's open up our terminal. And as before, we can activate our conda environment and then open up IPython. In order to start using NumPy, we are going to import NumPy, and as we learned before, we are going to import it as an alias called np. We're then going to use NumPy's arrange method, which we're going to cover a little bit later, and we're passing a range of 1 million values to it. Compared to that, we are going to use the regular Python functionalities. We're going to define a range with the values from 0 up to but not including 1 million. And we're going to use the list functions to create a list of those 1 million values. Now, once we've done that, we can multiply each of those values by 2. So going through all these 1 million values. And we're going to time how long that's going to take. So let's start out with multiplying the first entry here, my array, the one that we generated using NumPy. And this is going to start, and time it is going to take the time how long it takes in order to perform that operation. And here we can see the output, we can see the mean value and also the standard deviation. So the mean was 720 microseconds for the performance with a standard deviation of plus or minus 22 microseconds. Now let's do the same using the regular Python functionality. Here we're going to use time it again, and we're going to use list comprehension in order to multiply each value by 2, just as we did before for NumPy. And now we can see this took us 26.8 milliseconds with a standard deviation of plus minus 111 microseconds on a total of 7 different runs. So if we keep in mind that 1000 microseconds are 1 millisecond, we can see that the execution using NumPy was significantly faster. And in fact, the operation using regular Python took around 37 times as long. And depending on the operation, we will typically find that NumPy's operation are around 10 to 100 times faster than regular interpreted Python. So now that we understand that NumPy can perform operations significantly faster than regular Python and also uses less memory, let's cover the different aspects of NumPy. One of the key features of NumPy is working with n-dimensional array objects using ndarray, which stands for n-dimensional array. And those arrays enable us to perform mathematical operations on whole blocks of data using similar syntax to the equivalent operations between scalar elements. So to see how this works, let's open up our terminal again and let's dive into IPython. And we're going to start out again, of course, by importing NumPy using the alias np in order to save on typing. We're then going to use the array method, which is part of NumPy, passing 2 lists of values as an input. And we're going to store that in our data variable. Let's have a look at the data variable, and we can see we now have an array of values which are nicely formatted. Now, if we want to do any operations on those elements, such as int or float values, for instance, we can simply take our data variable and multiply that by a value. for example by 10. And this is going to multiply each individual element inside of our array object by that value. So here we can see that instead of having a value of 1.5, we now have a value of 15, minus 0.1 has been turned into -1, and so on and so forth. So it's a very straightforward and easy way to multiply each of the values inside of our array object by a certain number. We can also go ahead and simply add two of our arrays together, in which case we can also see the output here, so each of those values is basically multiplied by 2. Now an ndarray is a generic multidimensional container that has to contain elements of the same type. And every array has a shape, which is a tuple indicating the size of each dimension, and a dtype, so the data type of the object. So if we look at our data object here, we can go ahead and we can type in data.shape in order to get its shape. And here we can see it's a 2x3 array. It means we have 2 entries here with 3 elements each. And we can also look at the data type of our data variable by calling dtype on our data object. And we can see that it's of type float 64. So now that we understand what n-dimensional arrays are and that they're very easy to use, we can start out by creating our own ndarrays. And the easiest way to create an array is to use the array function that accepts any sequence-like object, including other arrays, and then produces a new NumPy array. So let's go ahead and let's first of all define a regular Python list, which is stored in our variable data1. And in order to create our array, we're going to use NumPy and we're going to call the array method on it, passing our list as an argument to it. And now if you have a look at our variable, we can see we generated a NumPy array. So it's really as easy as passing a list as an argument to the array method, which is part of NumPy. Now if we have a nested sequence, such as a list of lists, which have to be equal length, we can convert those into a multidimensional array. For that we're going to follow the same steps, calling the array method on NumPy and passing our list of list as an argument to it. Now if we take a look at the array we just generated, we can see we now have a 2-dimensional array with the individual lists that we had inside of our main list now being the different elements here. Now we can confirm that our array has 2 dimensions by calling ndim on our array object, and we're going to get back a value of 2 because indeed our array has 2 dimensions. We can also have a look at its shape as before, and we can see it's a 2x4 shape. Now unless a data type is explicitly specified, which we're going to cover a bit later, NumPy is automatically going to infer a suitable data type. So we saw the data type float 64 before. If you have a look at the data type of the new array, the 2-dimensional array we just generated, we see that we only have integer values inside of it. So therefore the data type is going to be integer 64. Now in addition to using the regular array function, there are also easy ways to create arrays of zeros or ones, and that can be very helpful if we want to use some matrix calculations later on. For example, we can use the zeros method, which is also part of NumPy, and then provide the number of elements we want to have as an argument. And here we generate a 1-dimensional array with 10 entries, which all are 0. We can also generate multidimensional arrays by providing the shape as an argument. So here we are calling zeros with a value of 3 and 6, and this generates a 3-dimensional array with 6 entries each, which are all set to 0. We can also use the empty method, which is going to create a new array of the specified dimensions without setting the values to any specific value. So they're going to be empty. But a quick note, it's not safe to assume that even though it's displayed as zeros, this is going to generally create an array of zeros. Now we also saw the arange method before when we compared the speed of execution between NumPy and regular Python. That is basically NumPy's version of the range function. And if we use arange with a certain argument, that's going to generate an array, and just as the range function generates a value from 0 up to but not including the provided argument, NumPy is performing the same action, but generates a NumPy array object. So let's have a look at some important NumPy array creation functions. We saw array before and also arange. We also created an array of zeros. In addition to that, we could create an array of ones using the ones method, or we could use sArray, which is going to convert an input to an ndarray, but does not copy if the input is already an ndarray. We also saw that we can generate an empty array, and in addition to that, we can use the full method, which is going to produce an array of the given shape and data type with all values set to the indicated fill value that we can specify. And then finally we have the I or identity method, which is going to create a square n by n identity matrix, which are ones on the diagonal and 0 elsewhere. And that's going to be very useful, especially if we dive deeper into linear algebra. The data type or D type that we saw before is a special object containing the information or metadata that the ndarray needs to interpret a chunk of memory as a particular type of data. When we work with NumPy arrays, we can specify the data type. So for instance here we are using the array method and we're passing a list that should be turned into an array, and we also specify the data type as an additional argument. So in this case we decide that it should be of type float64. In a similar way we can of course also specify that the data type should be of type int32. And if we now have a look at the data type, we of course get those specified values back. So float64 for the first object and int32 for the second one. Here's an overview of the different NumPy data types. We have type int or uint8, which refers to the signed or unsigned 8-bit integer types. In a similar way we have int16, int32 and int64, which refer to 16, 32 and 64-bit integer types respectively. And the difference between the signed and the unsigned version is that the signed version can contain positive and negative numbers, while the unsigned version can only contain positive numbers. So for example, a type of int8, a signed 8-bit integer, can represent integers from -128 to 127 inclusive, while the unsigned uint8 integer can represent 0 through 255. We can also use type float, float16, 32 and 64 as well as 128 for the respective bit versions. And there are also data types to store complex numbers, 64, 128 or 256. And we have data type bool, object, string and Unicode. We can also convert or cast one data type to a different data type. For this, let's have a look at an example. Inside of IPython, we can first of all create a NumPy array. And in our example here, we are passing a list of integer values. That means if we have a look at the data type of our array that we specified, we can see the default type int64 is being used. But if we want to cast this to a different type, to a float, we can go ahead and we can call the sType method on our array object and specify that it should be of type float64. Now if we take a look at our float array object, we can see that now every value has a dot after it because it's a float type. And indeed, if we call dtype on our float array, we can see that it's now of type float64. So we use the sType method in order to cast the data type from int64 to float64. And of course we can also do the reverse. So for instance, if we have a NumPy array consisting of floating point numbers, which of course by default are of type float, we could go ahead and we can call sType on our array object and cast it to type int32 for instance. And now we can see that whatever value we had after the decimal point is being removed. So instead of 3.7, we now have a value of 3. Instead of -1.2, we have a value of -1, and so on and so forth. So casting values to a different type can lead to some loss of information. Now let's see how we can perform arithmetic using NumPy arrays. Arrays are important because they enable us to express batch operations on data without having to use for loops, which can be quite slow. And when using NumPy, we would call that vectorization. So any arithmetic operations that we use, such as multiplying, adding or dividing values, which is being used between equal size arrays, applies the operation element-wise, so for each individual element. So let's jump into IPython and have a look at an example. We are starting out again by specifying a new NumPy array, which is a two-dimensional array using the array method. And of course we can have a look at the array, and indeed we can see it's two-dimensional and each dimension has 3 elements. Now we can perform some arithmetic using this array. For instance, we could multiply the array by itself. And since if we multiply an array by itself, of course both elements that we multiply have the same size, this would be applied element-wise. That means each of the elements will be multiplied by itself. So if we perform that operation, we multiply 1 by 1, which of course is 1. We multiply 2 by 2, which leads to 4, 3 by 3, which results in 9, and so on and so forth. We can also subtract the array by itself which of course will result in every value being 0 because we subtract each element by its own value. Now if we perform arithmetic operations with a scalar type, for example with an integer, that will be applied to each individual element. So for instance, if we divide 1 by the array, this will be applied to each individual element. So if we compare that to our array, instead of a value of 2, we would have a value of 1 divided by 2, so 0.5, and the same is true for all the other elements in the original array. And for instance, also if we square the array, this will also be applied to each individual element of the array. So while in the original array we had, for instance, a value of 4 and 5, once that is squared, those values will be changed to 16 and 25. Let's say we want to create a second array, which we are going to save in the variable array2. We can first of all have a look at array2, and then we can also use some comparison operators. For instance, we could check whether array2 is greater than the first array that we have. And when we do that, then each individual element will be compared between the different arrays. And of course, it's important that both arrays have the same size for this to work. So here we're going to check whether the first element is greater than the first element of our original array, and then we're going to repeat that for all the other elements. So is 0 greater than 1? That is false. So if we look at the result, we can see indeed the first value is false. Then we have the values true, false, and so on and so forth. We can also use indexing and slicing with NumPy arrays. And for one-dimensional arrays, it's quite simple, since that acts quite similar to Python lists. So for an example, let's jump into IPython, and we're going to use our arange function that we saw before to create a range, which we're going to store in our array variable. And this, of course, is going to create an array of the values from 0 all the way up to 9. Now, just as with lists, we can index into the different values. So for instance, if we pass index 5 to our array, then we're going to get back the 6th element. So that should be a value of 5 in this case. And similar to lists, we can also use slicing. So for instance, we can have a look at the values starting from index 5 all the way up to, but not including index 8. So this is going to get us back this section 5, 6, 7, because 5 is the position at index 5 and 8 would be the position at index 8, but it is exclusive when we use a slice, so therefore we're going to get back those 3 values. And we can also change the values. So if you want to replace the values of that array in the slice from index 5 all the way up to, but not including 8 with a value of 12, for instance, we can do that by a simple assignment. And if we then have another look at our array, we can see that from position 5 all the way up to, but not including index 8, we replace the values with the value 12. And we would call that propagation because the value is propagated for all of the elements affected. Now let's go ahead and let's make a modification to our array slice. So not to the original array, but to the slice which we generated. And specifically at index 1, so for the second value here, we want to replace that with a new value. Now this is of course going to update the values inside of our array slice object, but let's have a look at the original array. If we take a look at that, we can see that also in our original array, the values have been updated. And one of the reasons why NumPy works the way it works is if it were to copy the data, that could lead to some performance and memory issues and we would have to hold on to a lot of data. Now we can also use the bare slice to assign all the values inside of our slice to a specific value. So for example to 64. So if we now have a look at our slice, we can see those values have been updated to 64, all in one step. And if we look at our original array, we can also say that, of course, the original array has been changed accordingly. Now with higher level arrays, we have additional options. So in a two-dimensional array, the elements at each index are no longer scalars, but rather one-dimensional arrays. So for an example, let's create a new array, which we're going to call array2d. And let's have a look at the value at index 2, which of course is the third element inside of our array. And if you want to have a look at specific elements inside of one of the dimensions, we can go ahead and use such a nested approach. For example, here we are looking at the first dimension and then at the third element, which is going to give us back the value of 3. But there's also an alternative syntax. So instead we can simply use one opening and one closing bracket, and we can simply comma separate the entries. So this would be equivalent. We get the same value 3 as the approach up here. So in this figure here, we can see how we would index a two-dimensional array. We have two axes, and we can first index inside the outer elements, and then we can have a look at the second dimension inside of those individual lists. Now arrays can also be sliced like one-dimensional objects such as Python lists using the familiar syntax. So here we can see that we can simply use the starting and the ending index. The ending index is exclusive in order to create a subarray out of our original array. We can also slice two-dimensional arrays. So if we look at our two-dimensional array from before, we can for instance say that we want to slice from the beginning up to but not including index 2. And this is going to give us back this result. We're excluding the third sublist here because index 0 and 1 are the only ones that are going to be included in our result. So in this case, our array has been sliced along axis 0, which is the first axis. So we can select elements along an axis. So in this case here, we are basically selecting the first two rows of our array. We can also pass multiple slices. So in this example here, we are first slicing along axis 0 using the first two rows, and then we are slicing along axis 1 by excluding the first column and starting from the second column until the end. So this is going to give us back this result. We can also use some shorthand. For instance, if we just want to slice along axis 2, we can simply use a colon to say that we want to keep the entire axis. And then for the second axis, we just want to have a look at the first column. So only at index 0 up to but not including index 1. So this would mean we get back the first column of our array. So let's have a look at some examples. We can see, for instance, in this case, we are first slicing along axis 0 from index 0 up to but not including index 2. So that would remove the third row here. So we're only looking at the first two rows. And then on the second axis, we're going to exclude the first column because we're going to start from index 1. So we're going to skip index 0 and we start from column 2 to the end. So thereby we get this shape here. If instead we pass array with an index of 2, we're going to get the last row. And it's the same as if we were to pass a value of 2 for axis 0 and a colon, which simply means that we are going to keep all the columns along axis 1. And it's also the same as saying we are going to start from index 2 till the end because there are no additional rows in our array here, and we're going to keep everything along axis 1. In this example here, we are going to make no changes along axis 0 and for axis 2. So for the columns, we're going to start from index 0, but we're going only up to index 1 and excluding index 2. So therefore the first two columns here would be our result. And in this final example here, we are first going to have a look at the second row along axis 0, so this row here, and then we are going to exclude the last column. So we get this array here. And this is the same as if we were to say we are going to start at index 1 up to but not including index 2, which again is just the second row. And then again we are going to exclude the last column. We can also use Boolean indexing, which allows us to select certain entries in our arrays if certain conditions are met. And to see an example of that, let's jump into our terminal and let's define a new array which includes different names. And let's also create a two-dimensional array of data points. So if we look at our names array, we can see we have an array of different names. And of course we have our data array, which is two-dimensional. So let's suppose that every entry in our names array here corresponds to an entry in our data array. And of course for that to work, both the names array and the data array must have the same number of entries. Now we can simply do a comparison to our names array. And here we are checking whether names is equal to Bob. And this is going to look at each individual value in our array and return true if that element value is identical to the value we are comparing it to, or false if that's not the case. So here we get back true for the first value because it's equal to Bob, then false again, and true again because Bob occurs the second time, and of course all the other values are set to false. And we can use this Boolean logic and pass it as an index to our data array from before. So in that case we are going to get back all the respective positions in our data array where names corresponds to Bob, so would evaluate to true. So if we have another look at our data array, we can see that our result was the first entry here, where the entry for names is equal to Bob. And then that was also true for the fourth entry, which is exactly the second result returned to us. Now, of course, we can build on top of that and also index the column. So we are basically looking at axis 1. And in this case, we are going to exclude the first column and just starting from the second one. So we only get back 7 and 0. If instead we want to select every value but Bob, we can change the comparison here and say we want to get all the results back where name is not equal to Bob. So in this case, everything that was true before is now false and vice versa. Or alternatively, what we could do is we can take the comparison from before, so names equal to Bob, and we can use a tilde in front of it, and that's going to work as to negate the result. So the result would be the same as if we were to compare it to not be equal to Bob. So let's take that as a basis and let's have a look at our data array. And let's use Boolean indexing to check for the data sets where the name is not equal to Bob. And then we're going to get back all the other values where the name is not Bob. Now we can also chain our conditions together. For instance, if we want to check whether the name is Bob or the name is Will, we can simply use a logical OR to combine these two conditions, and we're going to store that back in mask. Now if we look at the result, we can see we get a value of true, false, true, 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 false, false back. And if we just verify that with our names array, that is the case of course because we have Bob and Will in the respective positions. And as before, we can get the corresponding results of our data array back by passing mask as a Boolean index, and we're going to get back the corresponding data pairs at those specific positions. Now finally, we can also use fancy indexing, and that is a term adopted by NumPy to describe indexing using integer arrays. And for an example, let's assume we have an 8x4 array, which consists of zeros. And we're going to use a simple for loop to change the value of each row according to the respective row's index. So if you have a look at our array now, we can see that for row 1, all the values are 0. For row 2, all of them are 1, and so on and so forth. Now to select a subset of the rows in a particular order, we can simply pass a list or ndarray of integers specifying the desired order. So for instance, we can say for our array we want to start with the row at index 4, then index 3, then index 0, and then index 6. So if we look at the result, we can see that is exactly the order we get back here. And as we already saw before, we can also use negative indexes to select from the end. So here we would start at -3, then -5, -7, and this corresponds to the appropriate rows starting from the end of our array. Now if we pass multiple index arrays, this does something slightly different. It selects a one-dimensional array of elements corresponding to each tuple of indices. So as an example, let's say we are going to use NumPy to create a range from 0 to 31, and then we're going to reshape that with a tuple of 8 and 4, and we can have a look at our array that we created. So here we can see our range from 0 to 31 has been created, and we have that split up in 8 rows and 4 columns. And now we can use fancy indexing to make a selection. So here, for instance, we are starting with row with index 1, which is a second row, and in the second dimension we are going to select the value at index 0, so that would be 4. Next up, we're going to select the row with index 5, which would be this row over here. And specifically, we're going to select the element at index 3, which would be 23. And we continue to do that for 2 additional elements. So if we look at the results, we can see that we get back 4, 23, and then 29 and 10. Now we can also transpose arrays and swap axes. Transposing is a special form of reshaping that returns a selection of the underlying data without copying anything. So let's open IPython and let's have a look at an example. We're going to create a range from 0 to 14, and then we're going to reshape that so that we have an array that has 3 rows and 5 columns. And if we want to transpose our array, so switching the rows and the columns, we can use the capital T attribute. And if we have a look at that, we can see that now the rows and columns have been transposed. So now we have 5 rows and 3 columns. And when we're doing matrix computations, we may transpose our matrices quite often. For example, when we are computing the inner matrix product using the dot method, which is part of NumPy. So as an example, let's create a new array, which if you look at it, has 5 rows and 3 columns. And we can use the dot method to multiply the transposed matrix with the actual matrix to generate the inner matrix product. And using simple transposing using the capital T attribute is a special case of swapping axes. So instead of doing that, we can call swap axes and specify which axis we want to swap. So axis 0 and axis 1. And this is going to have the same result so that the columns here turn into the rows and we are transposing our array. We can also use NumPy to generate pseudorandom numbers. For that, NumPy provides a random module, which supplements the built-in Python random module. Let's have a look at an example and let's use the random module as part of NumPy to create a 4x4 array of random numbers. So once we generate that, we can have a look at our samples objects we just created, and all of the entries in our array are randomly generated. And in contrast to Python's built-in random module, NumPy's random module generates random numbers for each of the values in the array, while the built-in Python random module would only generate a single random number. To compare both random methods, let's actually first import normal variate from the Python random module, and let's specify a variable n that has a value of 1 million. Now we can first have a look at Python's built-in random module. We're going to use list comprehension here using the normal variate method as part of Python's built-in random module, and we're going to time how long it will take to generate 1 million random numbers using Python's built-in module. So we can see in this case it took 375 milliseconds as a mean value out of 7 runs, with a standard deviation of 9.18 milliseconds. Now let's compare that to NumPy's random module, which is going to use the standard normal method, which is a method as part of NumPy's random module. And again, we're going to pass a value of 1 million to it. Now here we can see it only took 14.4 milliseconds on average as a mean out of 7 runs, with a standard deviation of 140 microseconds. So in this case, it was around 26 times faster to use NumPy's random module. Now those numbers are not truly random, but they're rather pseudo-random. And if we want to get back the same number for several runs, for example, if we are testing some code, we can provide a seed. So here we are defining a variable RNG. We're using the random module and we're passing a seed argument to it. And when we pass the same seed value, we're going to get back the same number. So here we can use a randomly generated number and create an array based off it. And if we look at its value, we can see we get back those different values. And if we now generate a second object, array2, with the same seed, and we generate a second variable data2, which is taking our randomly generated number, and again we are using that to generate a 2x3 array, and we have a look at that array, we can see we get back the exact same numbers, even though this is a different number that we generated. The reason is we passed the same seed to it. And there are a number of different NumPy random number generator methods. For example, we can shuffle the numbers to randomly order the different values. We can use standard normal, which we used before, to draw samples from a normal distribution with mean 1 and standard deviation 1. Or we can use normal, for example, to draw samples from a normal distribution. We can also work with universal functions, also called ufuncs, which are functions that perform element-wise operations on data in arrays. And we can use them to, for example, create the square root or to work with exponents. So to have a look at an example, let's switch into IPython and let's create a range using NumPy of the values from 0 to 9. Now we can just use the square root method, which is part of NumPy, which is a universal function, and we pass our array as an argument to it. And then for each of those elements inside of our array, the square root will be applied. Now that's an example of a unary universal function. We of course also can work with universal functions that take, for example, 2 arrays as inputs. For that, let's create 2 variables, x and y, and for that we are using the standard normal method. And we can have a quick look at the values of x and y, and both of them have the same length. So if we want to get the maximum value out of those respective array datasets, we can use another universal function the maximum function, and this is actually taking two arguments, x and y, and it's going to give us back the maximum value out of the two arrays. For example, out of minus 1.36 and minus 0.46, the second value would be larger, so this is going to be added to our result. When we compare 0.64, this is larger than minus 0.06, so therefore the first value would be added, and so on and so forth. And there are a lot of different unary universal functions available, for instance to get the absolute value, the square root, or the square. And of course we also have a lot of binary universal functions. We just worked with a maximum function, but we can, for example, add two numbers, subtract two numbers, or multiply them. When we use NumPy, we can express many kinds of data processing tasks using arrays instead of having to write loops. And the fact that we can replace loops with array expressions is referred to as vectorization. And vectorization is generally much faster than working with loops. So let's say we want to evaluate the function square root of x squared plus y squared. For that we can use our arange method, and we can start from -5, go up to 5 in steps of 0.01 values. So this is going to create 100 equally spaced points. We can then use the mesh grid method, which takes two one-dimensional arrays. In this case we pass points to it twice, and it's going to produce two two-dimensional matrices based on that. So if we look at one of those two generated matrices, we can see that we have a number of rows going from -5 all the way up to 4.99. And now we can go ahead and use the square root method to calculate the square root of those two matrices, one which we see here and the other one generated, which are squared. And to visualize the results better, we can use matplotlib. So let's import plt from matplotlib.pyplot, and we can then generate an image that's going to display our data. We can specify a color bar, and we can also specify a title. And we can then see a graphical representation of our data. We can also use NumPy to work with file input and output. NumPy is able to save and load data to and from disk in some text or binary forms. Now for loading text or tabular data, most users would prefer working with pandas or some other tools. Therefore we're going to focus only on NumPy's built-in binary format. And specifically we can use the save as well as the load method, which is part of NumPy, in order to save and load data. Let's jump into IPython and have a look at an example. We can start out by using our arange method to generate a new array. And to save our array to disk, we can use the save method. We're going to specify the name, and of course we also need to pass our array as a second argument to the save method. Now when the file is saved as some array, automatically the file ending .npy is going to be added. Now if we later on want to load our file, we can use the load method, and of course we need to specify which kind of file we're going to load. We can use the savez method in order to save multiple arrays at once, and that's going to save the file in an uncompressed archive that we specified before. And when we load the npz file later on, we get back a dictionary-like object. So if we're going to load the file that we saved before, we can then reference the individual arrays that we want to load. And for that we are going to simply index into that specific argument. So for example into b. And that's going to give us back the specific array that we saved. NumPy can of course also be used for linear algebra. So if you want to work with matrix multiplication, decomposition, determinants, or for instance square matrix math, NumPy can be really useful. To see that in action, let's start out by defining a new array. And let's define a second array y with different values. Now if you have a look at these two arrays, our array x and y, we can see that the first one has 2 rows and 3 columns, while the second one has 3 rows and 2 columns. And therefore we can multiply the two matrices together if we wanted to. For that we can use the dot method, x.y, and this is going to multiply the individual elements of our matrices together. And this is going to generate a new 2x2 matrix with the multiplied values. Now instead of writing x.y, we can instead use the dot method and just pass x and y as an argument. There are a lot of linear algebra methods available as part of NumPy. Here's a quick list of the most commonly used ones. Here we can see the dot method we just used before, and in addition to that we can, for example, compute the inverse of a square matrix, or for example, compute the sum of the digital elements using the trace method. Now let's finally have a look at a random walk. Now a random walk provides an overview of random steps taken, and that can also be visualized. And using regular Python, it's possible to model such a random walk. We can import the random module, specify a position as well as a walk list and a number of steps, and then we can loop over the range of steps. So we would loop 1,000 times, and then we can determine the individual positions of our random walk. Here, for example, we are generating a random integer 0 or 1, and this is going to infer whether we take a positive step or a negative step. And we are going to append each individual step to our walk list. If we then later on plot the result, we get something like this, where we have positive steps and negative steps, and that simulates a random walk on this graph. Now we can do something very similar in NumPy. For that we can start out by defining the number of steps, and then we can use NumPy's random method in order to generate a new random generator. In this case we specify a seed, so we can reproduce the result later on if we want to. And then as part of our random generator we are going to use the integers method, passing the number of steps as an argument to it. We can then decide whether we want to not take a step, a positive step or a negative step using the where method. We then need to take our steps, call CumSum on it and add it to our walk. And then we can infer the minimum value, which in this case would be -8, as well as the maximum value, which is 50 in this case. And such random walks have many applications, for example in engineering, computer science, but also in psychology, biology and economics, for instance. We learned how we can use NumPy for numerical computations, and we covered the most important functions. In the next video we are going to learn about pandas. If you want to follow along, feel free to subscribe to the channel, and see you guys in the next video.